So here is Euler's way of succinctly summarizing his solution. If you are given a connected graph, we just look at how many vertices in it have an odd degree. If that number is more than 2, that is, if it is 4 or 6 or more, then there cannot exist an Eulerian cycle or an Eulerian path in it. If, however, the number of vertices with an odd degree is exactly 2, then the graph will have an Eulerian path that starts from one of these two vertices and ends at the other vertex. And if finally there are no vertices with an odd degree, then the graph will have an Eulerian cycle. And because a cycle can start and end at any point, in other words, there is no well-defined starting or ending point for a cycle, you can imagine undertaking a journey along the Eulerian cycle from any vertex you want. And Euler says, with these rules, the given problem can also be solved. So this solution applies to any general connected graph, okay, connected undirected graph. So let me end this section by showing you a poem about this problem. Some citizens of Königsberg were walking on the strand beside the river Pregel with its 7 bridges spanned. "O Euler, come and walk with us," those burghers did beseech. "We'll roam the 7 bridges over and pass but once by each." "It can't be done," thus Euler cried. "Here comes the QED. Your islands are but vertices, and 4 have odd degree. From Königsberg to Königsbuck, so runs the graphic tale, and still it grows more colorful in Michigan and Yale." By the way, Königsbuck is the first book that was published on graph theory in 1936, 200 years after Euler solved this problem. And QED here is just a Latin phrase which means thus it has been demonstrated or thus it has been proved. So Euler not only came up with the solution to the problem, he also furnished the proof. And one of the reasons why graph algorithms are considered to be the hardest algorithms to work with in a general course on algorithms is that it is often not easy to prove the algorithms as correct. So remember that when you come up with any algorithm, the first thing you have to demonstrate is that the algorithm is correct. Then you start worrying about whether it's efficient or not. Can we make it more efficient? But if it's not correct, then efficiency, it's pointless to look at efficiency, right?